Okay, so last time we did section 8.3, which was confidence intervals for means. The time before that we did confidence intervals for proportions. Today we're going to do sample size calculations, and this will be the last section that we do in chapter 8. We don't do section 8.5. In my first class this morning, I did not quite finish section 8.4, and if that happens in here, then I'm probably just not ever going to teach that part of that section. It's just one like extra topic that he throws in, sort of out of place, but I may get to it today. But before I start on that stuff, let me open it up. Are there any questions about confidence intervals for proportions? I'm sorry, for means. Where do you go on your calculator to do those? Stat, then test, then t-interval. T-interval. So from now on, and I mentioned this before, from now on, every problem that you work, the first thing you should do is ask yourself, is this a proportions problem or is this a means problem? And if it's a proportions problem, there will be, as we go through the semester, there'll be other questions that you ask. Is it a one sample or is it two sample, that kind of thing. So far all we've done is one sample. So proportions are 1 prop z int. Chapter 9 we'll get hypothesis tests, and we'll add to this. A means, for now, all we have is t-interval. I'm still getting email questions from people once in a while that say, I don't know how to compute this confidence interval. I went to 1 prop z int and, well, you should have went to t-interval. This is a means problem, that kind of thing. So just make sure that you know that each of these only applies in that particular area. Don't try to use it at the wrong time or it isn't going to work. Any questions over the t-interval stuff? All right. Then we'll go to section 8.4, and 8.4 is sample size calculations. So I'm going to leave those there. But we're going to do like some scratch paper stuff over here. Okay? So sample size calculations. As a practicing statistician, I still do a lot of consulting on research projects and things like that. And probably half of the time when somebody comes to me with a question, it's to do a sample size calculation. Right? They think about it. If I'm going to do research, I need to know how big of a sample do I need. And I keep telling you sort of jokingly that small sample bad, big sample good. Right? Well, how big is big enough? That's the question. Okay. So sample size is one of the most important parts of the design of any study. Observational or experiment, doesn't matter, the design of the study, no matter what, the sample size is one of the key parts. Now what you'll do in this class is the absolute most simple sample size calculation that there is. We're going to calculate the sample size needed to do these confidence intervals. Right? And that's all based on margin of error. Remember when we talked about confidence intervals for proportions? And we used some examples early on where I said, well, the 95% confidence interval is from 0.2 to 0.8. That's not a very useful confidence interval, is it? The true population proportion is somewhere between 20% and 80%. Can't you do any better than that? Yeah, you can if you take a bigger sample. Right? If you want to shrink the margin of error, you need a bigger sample. So that's how sample size calculations get done in the simplest case of confidence intervals. If you come to me as a statistician and say, hey, what size sample do I need? I'm going to say, well, how much error are you willing to live with? How close do you want to make sure you are to the truth? If you say, well, I'm within 10% of the true population percent, that's good enough, then that tells me, oh, they want a margin of error of 10%. I can use that then to set a sample size for proportions. If you say, no, I need to be within 1%, first thing I'll do is raise my eyebrows like, ooh, that's going to be expensive. A 1% margin of error means you got to have a huge sample. Probably 5,000, 6,000 people in your sample to get a margin of error that small, right? So sample size calculations, the mathematics, the arithmetic can tell us what the sample size needs to be, but you have to weigh that with practical concerns. Like it's very often that I'll do a sample size calculation for somebody and they'll go, ooh, we can't do that. We don't have that much money. Or there aren't that many patients. I'm working on a project right now with a company that does, has a product for RSV, which is a virus. It causes pneumonia. And if it's in transplant patients, they're immunocompromised, right? So they're real specific. These are people with bone marrow transplants and in a certain age range and all that. So they're very specific. And the sample size calculation came back at 300 and some patients. And I said, you know what, that would take us 10 years to come up with that many patients. So, okay, well, we're going to have to change the study then, change the design. So sample size calculations have to be weighed with practical issues of resources. So it's kind of a balancing act sometimes. So how do we do it? Well, we're going to start with proportions and then we'll go to means. But remember that a margin of error, which I call MO, but for purposes of these calculations, I'm going to shorten that to M, so I don't have to write that whole thing out all the time. Right? So the margin of error we're going to call M. We know that in a proportions problem, for a confidence interval in a proportion, the margin of error is the part you add and subtract. Right? You start with p hat, and you add and subtract the margin of error. So what is that margin of error? What goes into it? Okay. Remember, it's p hat plus or minus. I heard somebody say square root. So yeah, it's got a big square root. P hat, 1 minus p hat over n. And what goes out front? The z-score, the z-critical value, right? So I'm just going to put z right there. And z is just number of standard errors. This is the standard error. So z tells me how many of those standard errors I need. So multiply it by z. And if we want 95% confidence, what is that z?
1.96.
1.96. If I want 90%, it's 1.645. And if I want 99%, it's, you have these memorized by now, right? 2.576. And you don't have to have memorized because you get a cheat sheet. So you can write those, and those are the big three. Those are the only three you're going to need on a test. So if you tell me what size, if you ask me what size sample you need, then this equation has an n in it. I can solve for n. And you're thinking, ooh, algebra. I liked algebra. Right? Solve this for n. Let's just do that. Okay, divide by z. So I divide both sides by z. On that side, they divide out. I'm left with that. Now the n is inside of a square root. So you square both sides to get rid of the square root. So square both sides, and I got m squared over z squared equal p hat 1 minus p hat over n. Okay? Multiply the n over to here, because it's in the bottom and we don't want it in the bottom. We want to solve for it. So I'm going to multiply through by n and get rid of that. And then, we're doing a lot of steps at once. Divide by the rest of this, so I can multiply through by z squared. So I'm going to start a new line. Z squared times p hat times 1 minus p hat all over. I'm going to divide out the m squared. So I'm doing two steps at once. I'm dividing the m squared and I'm multiplying by the z squared. Everybody following me? No. No? Okay. Back to here. If you have a fraction equal to a fraction, what can you do?
Multiply by the denominator.
Okay, cross multiply, right? Remember doing that? So I'm going to cross multiply and I get n times m squared equal z squared times that, right? So I come down to that equation. Now solve for n.
Is there a function in our calculator for this?
Actually, no, there's not. Dang it. So divide by m squared. So I divide both sides by m squared. And I get this formula. So there's the formula for the sample size, right? Now, formula, that means that you've got n expressed as a function of three variables over here. Z, p hat, and m. And by the way, the book doesn't have the hat on the p, but that's okay. It really means the same thing. They just have a p. But if they had a p in there, where are you going to get that p? Why are you doing this study in the first place? To estimate p, right? Well, if you're trying to set the sample size before you do the study, you don't even have an estimate of p. So you don't have p and you don't have p hat. What about z? Where do you get z? That you have. Right? If you ask me, hey, Mr. Statistician, what size sample do I need? I'm going to say, what level of confidence do you want? You say, well, I want 95% confidence interval. Okay, that tells me what my z is. So that's not a problem. Getting z is not a problem. If you want 95% confidence, it's 1.96. That's those other numbers we spouted a minute ago. This m, where do you get m?
Margin of error.
That's the margin of error, and again, you just specified it. I'll say, what amount of error do you want to live with? Well, I want to be in error by no more than 5%. Okay, then the margin of error is 5%. So in here, m is a proportion, not a percent. So if you say 5%, that means 0.05 for margin of error. Okay, and that's a key thing that I'll demonstrate in a second, that if you make that mistake, you'll have really bizarre answers. The only thing left is this p hat. So where do you get an estimate of p hat before you've ever conducted the study? That's a problem. So what they tell us is use the best estimate available for p hat. Oftentimes, that will come from a previous study conducted on a similar population. The example we're going to do in a second talks about a study that was done on binge drinking among college students. Everybody knows what binge drinking means, right? Going out and getting hammered on Friday night, but the rest of the week you never drink a drop. Right? That's binge drinking. Right? Well, college students are known for that, unfortunately. So if you're going to do an estimate or going to do a study in binge drinking, say you're interested in doing a study at Washburn University, and you find out, well, you know, a couple of years ago they did a study at Emporia State. That's a similar institution to Washburn, and their percent who binge drink was 25%. Actually, I went to Emporia State. I know it's much higher than that. Let's say 44%, right? Which is, I think, the number in the example that we're going to do. So you use previous research to estimate this. So that's one way you can get it. Another way you can get it is from a pilot study. What do you think that means, a pilot study? Nobody has an idea of pilot study? Basically, all that means is it's a small study that you conduct first as just get an idea of what's going on, then you'll go and do a big study, right? Sort of like a practice study. And a lot of times the results of the pilot study get kind of incorporated into the big study. So we're going to look at the first 20 patients in a study, and then once I get information from them, that'll help me design the full study, and I'll use those 20 patients, plus I'll add another 150, or whatever. Okay. So pilot study, so published studies, pilot studies, educated guesses, things like that. That's where you're going to get an estimate of the P. Now suppose I want to do a study to estimate the proportion of college students that carry a concealed weapon. Right? Do I have an idea of what that number might be? No, but I really hope it's not 80%, right? And I really think it wouldn't be. I think it would be far below 50%. I doubt half of you are sitting in here with a handgun. I hope not. Right? So I really have an educated guess that that number is going to be 10% or lower. Right? So I can probably make a reasonable educated guess as to what I think it's going to be. If you have no previous information at all, if no info for p hat, use p hat equal 0.50. Because for proportion, you know that, well, it can't be less than 0, and it can't be bigger than 1. And 0.5 is right in the middle. And mathematically, I'm not going to bother to do it for you, but mathematically you could show that considering that n is a function of p, and considering these two as fixed numbers, as a function of p, this is a quadratic, or a parabola. Remember that from algebra class? If I distribute this p, I got p minus p squared. So I got a p squared term, and it has a negative in front of it. So what does that tell you? It's a parabola that opens down. So it has a maximum, right? So the maximum sample size will occur at the middle, right? And the middle, if you remember your x-intercepts kind of thing, you're going to get an intercept of 0 and an intercept of 1. So halfway between those is going to be where the max occurs, and that's at 0.5. So I said I wasn't going to do it, and then I did it. The maximum is going to occur at 0.5, so this maxes in. Why would you want to maximize your n? Well, then you know you're covered. If you say, well, I want a margin of error of 5%, and I have no idea what the proportion is going to be, I'll use 0.5, and then the n that I get from that calculation I know will be big enough no matter what p is. Okay? So it's being conservative. Right? So that maxes your n. So some of the homework problems that we'll do, and I'm going to do an example here in just a second, it will say, work this in two ways. Use this previous study to give you an estimate of p hat, compute the sample size. Now do it as if you don't have any previous information and recompute the sample size. And you'll see that the sample size goes up when you use 0.5. Okay. So let's do that. I'm going to turn to the homework at the end of section 8.4, which starts on page 394. And let's look at the binge drinking study, which is actually two studies, or two of the problems, 847 and 848. And I'm going to do 848, but it refers back to 847. So I'll kind of paraphrase that rather than read verbatim. But it talks about a study at Harvard School of Public Health, and this was an actual study that was done, found that 44% of college students were binge drinkers. Okay? 44% were binge drinkers. A study at the University of Minnesota plans to estimate the proportion at their school. Then 848, which is the one that I'm going to work, refers back to that and then says they estimated that 19% of college students were abstainers. What does that mean? They don't drink, right? They don't drink. So notice that 44% and 19% don't add up to 100%. So there's some other category. So you can be a binge drinker. You can be a drinker without being a binge drinker. Right? So that's the rest of it. but 19% are abstainers. It says, estimate, to estimate this proportion in your school, how large a random sample would you need to estimate it within 0.05 with probability 0.95? Huh?
94%
That's what that says. With probability 0.95, well, they're kind of disguising it, but what they're saying is use 95% confidence level. So with probability of 0.95, that's telling me what I need to use for my Z. Okay? So I'm going to put that formula over here under proportions. N equal Z squared times P hat times 1 minus P hat all over M squared. Now we're going to work this problem. Part A says you are unwilling to predict the proportion value at your school. So they gave us this 0.19, this 19% from the Harvard study, but Part A says ignore that. You're not willing to say that that will apply at your school. So if you're unwilling to use that, what do you use? 0.5. So we're going to fill in 0.5 for P hat. So I got 0.5 times 1 minus 0.5, and my Z out front, 1.96, because they said with probability 0.95. Now don't forget, that is squared. And if you look around the room, you'll probably see 3 people that will forget to square it on the test. When I look at their cheat sheet, they'll have the formula right on the cheat sheet. But when it comes down onto the test, they don't do what the cheat sheet says to do. Right? Now you get to use the cheat sheet, at least do what it says. Right? You know what's worse, though, is when I look at somebody's cheat sheet and they have the formula wrong on their cheat sheet. And that does happen. But man, don't ever do that. It's just a formula. I don't make you memorize formulas, which is why I let you have a cheat sheet. So just make sure that you have the formula correct on your cheat sheet. Okay, now the only thing I'm missing now is the M on the bottom. And what's the M? Margin of error. Did they use the words margin of error? No, dang it. Wouldn't it be nice if they just say, the margin of error, M is this, and they just spell it out for you? Well, that's not real life. In real life, people don't talk like that. They say, you want to have estimate it within 0.05 with probability 0.95. People talk like that, right? Not really. But what they would say is, you want to be in error by no more than 5% or 0.05. So that's your margin of error. 0.05, and remember, that is squared. So don't forget to put the square on that also. Now do that on your calculator. I'm going to write up here that this is problem 848, so that you know in your notes that where these numbers came from. Anybody got it yet?
384.16.
384.16. Okay. Now, what is that number again?
Sample size.
Sample size. That's N, right? That's the number of people I need to ask. So I can find 384 people, but it's this 0.16 guy that I'm looking for that's hard to find. So what do I need to do? The answer needs to be a whole number, right? Well, some textbooks would say if there's any fraction left over, you need to go up to the next whole number. But our author says, oh, just use whatever number's closest. So round off. Instead of round up, you round off. So this would round to 384. In practice, that's really no practical significance. Right? If I use 385 or I use 384, it really isn't going to affect my estimate very much. But on the online homework, it affects whether you get it right or not. Because if you put 385 in there, it'll say, nope, sorry, you missed it. Here's the formula. Well, I know the formula. I just rounded wrong. So round to the nearest whole number. That should be 384. Okay? That's part A. Part B says, now do the same thing, but use the Harvard study as a guideline. So what changes in this? The p hat changes. So I still have 1.96. It's still squared. Now I have 0.19 and 1 minus 0.19 instead of 0.5. The 0.05 on the bottom is still there. They didn't change the margin of error. Do that one on your calculator. Question?
Sorry, I don't understand where the .19.
Okay, just read the problem.
Oh.
It says, the Harvard study mentioned in the previous exercise estimated that 19% of college students abstain from drinking alcohol. So that's where if you're trying to estimate the proportion of abstainers, that's your best estimate of, is use some other study at a different school. Okay? Logan, you got it?
236.49.
Okay, so n equals 236. Notice that that number is smaller than this number. And it's quite a bit smaller. 236 up to 384. A question came up in my last class that why would you ever do it this way? Why don't you just always do this if it's conservative? You know you'll have a big enough sample size, just always use that. And the answer is, if the subjects are easy to get and they don't cost you much, then sure, use that. But in a lot of studies, it may be very expensive to track these subjects down. Each subject may cost you $100. Well, if you have $100 and you added how many extra people? About 150, right? You add an extra 150. 150 times 100. That's a lot of money. It's a lot of extra money. So if you're pretty certain that your P is going to be quite a bit smaller or quite a bit bigger than 0.5, then use it because it'll save you a lot of resources. If you really don't trust any previous estimates, then go with the 0.5, but that's worst case scenario. Okay? Everybody understand how to do that? Now suppose they reworded this and they say 19%, right? And then what if they, instead of being nice like they were, and they say, you need to estimate it to within 0.05. What if they said, you need to estimate it to within 5%? Because they talk about 19%, estimate to within 5%. What do you suppose a really common mistake there is?
0.5.
Putting 5 in there instead of 0.05. Because you say, well, 5%, my margin of error is 5. So you put a 5 in there. Redo this calculation with a 5 in there instead of a 0.05. Let's make that mistake so that when you do it on the exam, you'll recognize and go, oh, I made that one mistake. What'd you say?
9.4.
It actually should be
.03.
it should be this same number, but with a decimal moved. 0.0236. Yeah. Right? And trust me, I've seen this over my teaching career over and over again, and people write that down and they say n equal that, and they're just happy as a lark and they go on to the next problem. Think about it. Does that make sense? If you went to a statistician and said, hey, tell me what my sample size needs to be. And they say, well, I round to the nearest whole number, I get what? 0. Or 1 if you went up. So you tell me I only need to ask one person and I can estimate this to within 5% margin of error? Woohoo! It's going to be easy research. It makes no sense. And if you round to the nearest whole number, you're just down to 0. Ooh, I don't need to ask anybody. I can just make up a number. And I'm guaranteed it'll be within 5% of the truth. That makes no sense, right? So if you make that mistake, the magnitude of the problem is huge because you're off by a factor of 100 squared. So you have a huge mistake. Catch those kind of mistakes. You have to be able to recognize, well, that can't be right. Okay? And then pretty quickly you figure, oh yeah, that's that one mistake he talked about. So if you get an answer that is nonsensical too small, then you know that was the problem. Now what happens is, when we go to means problems, instead of estimating p hat, we have to estimate the standard deviation, and people start making that mistake there. They say, oh, I remember he said I have to move the decimal place. So they'll move the decimal on a standard deviation. Well, that's not a proportion. You don't do that. So be careful. Don't mix the two things together. So I'm going to leave the formula there. I'm going to erase all this stuff so I can recapture board. And I'm going to go to means problems. So doing the same thing with means instead of proportions, I'm not going to do all the algebra all the way through this time because you've seen it. And you can just trust me that the answer is correct. But tell me what the margin of error is in a means problem confidence interval. What's the add and subtract part?
T
A t times the standard error, which is
standard deviation.
standard deviation, which we call S,
Over square root of n.
over the square root of n. So there's your margin of error, right? Now, just like the last one, I paused at this point. Well, actually, I haven't done the algebra yet. I'm going to do the algebra here and just say what the answer is, but don't write it down because it's wrong. And then we're going to fix it, okay? So, n, doing all the same algebra, is t squared s squared over m squared, right? That's doing the algebra, solving for n. But what's wrong with this? What do we need to fix? Well, let me ask you this. Where do you get this t critical value? Back of the book. And when you go to the back of the book, you see a table, and how do you find the t that you need? You go down to what?
One below the number you have.
Okay, and that's degrees of freedom, right?
N minus 1.
Which is n minus 1, right? So you have to know n to look up the number. Well, we're trying to find out what n is. We don't know what n is. So I can't go to the t table because I don't know n. So I can't use a t. So what do? Well, we say, well, I guess we can't use a t. Let's use the z. And it'll be close. Right? It'll be close. The only time it's way off is when you have really small samples. But remember, after you get it to a sample of, say, about 30, then the t and the z are so close together it isn't going to make any practical difference in your sample size. So we just use the z. Now some statisticians will say, well, I do it in 2 steps. I start with a z, I get a sample size, then I say, okay, now I'm going to use that to compute my degrees of freedom and go back and replace the z with a t, and it'll up your sample size by a few. But we don't bother with that in this kind of a class. So we can't use a t, so we use a z there. Okay? So now it's fixed. That is the formula, so I'm going to write it over here. N equal z squared s squared over m squared. But we still have a problem. What is this s? Standard deviation, right? How do I know the standard deviation before I've done the study? Same thing as with that proportion. Sample size calculations are spooky things. Right? It's close to Halloween. It should resonate with you. They're spooky because it's really guessing. I don't know what this p is, but I'm going to make a guess. If I guess wrong, my sample size is going to be off. I don't know what this s is, so I'm going to guess. And it's the same exact thing. Use your best estimate available. Now I'm going to say, instead of for p hat, I'll say for s. But the same argument. You use previous studies that used the same variable and look at, well, what standard deviation did they have? And you can use that. If you did a pilot study, you'll have a standard deviation on that variable. You can use that. If you don't have either of those things, maybe you make some kind of educated guess. Right? That's harder to do with standard deviations than it is with proportions. When all else fails with proportions, we used 0.5. We can't do that with standard deviations. Why not? Well, standard deviations are numbers that have to be bigger than 0, but there is no upper limit. For proportions, they had to be between 0 and 1, so I used the middle. For standard deviations, they have to be between 0 and infinity, so use the middle. The middle is still infinity. You can't. So you have to come up with an estimate. And when I do sample size calculations for people, and I ask them that question, you can just watch their eyes glaze over. It's like, okay, I need to know what margin of error you want. And they can kind of come up with an answer for that. Okay, I want it to be within 3, whatever. Okay? And what's the standard deviation? What's the estimate of the standard? The what? The variability. How much variability do you expect? I don't know. Where do I get a number like that? And they have no idea. So then it's kind of really up to the statistician to look and try to find estimates in the literature or something that you can come up with. Right? So it's tough. If all else fails, you can use the, quote, range rule. And I've had to use this a time or two, but it's not very common that it comes to this. The range rule, let's look at actually, no, I'll finish that discussion. Let's look at problem. I'm kind of getting ahead of myself here, so I was going to bail out and let's do an earlier one as an example, then we'll come to this one. But since I already wrote it up here, problem number 852 in the book, it says income of Native Americans. How large a sample size do we need to estimate the mean annual income of Native Americans in Onondaga County, New York, whatever that is, correct to within $1,000 with probability 0.99. Okay? The correct to within $1,000. Okay, this is their annual income. So what are they giving me there? When they make that statement, correct to within $1,000. That's the margin of error. So in my formula, that becomes my M. So on the bottom I have 1,000 and then squared. That's the margin of error. Then they say with probability 0.99. What are they giving me there? Confidence level. So they're saying use 99% confidence for your interval. Okay, now what Z do I use for 99% confidence? 2.576. In the book, in his solutions and things, he would use 2.58, but I stick with 2.576. But again, when you're doing sample size, you're going to round to the nearest person anyway. That difference, 2.58 versus this, isn't really going to make a practical difference. So the only thing I'm missing is this S. So keep reading. It says, no information is available to us about the standard deviation of their annual income. But we guess that nearly all of the incomes fall between 0 and $120,000. Basically, they're saying, well, I know that no one in that county makes more than $120,000 a year. So they gave me the range. The range was 0 to 120,000. Now I can use that as a real crude estimate of standard deviation. And here's how it works. If I draw a normal distribution and use the empirical rule, what they say, let me read it again, because I didn't quite read it the way it says. We guess that nearly all of the incomes fall between nearly all. So 99.7%, and how many standard deviations do you go to get that? 3 in each direction, right? So what they're saying is 0 and 120,000 are 3 standard deviations from the mean. All or nearly all of the incomes are between them. So that spans a distance of how many standard deviations? 6. So this distance all the way to there is 6 standard deviations. So I take that distance and I divide by 6, and I got an estimate of standard deviation. So the range rule is you take the max, subtract the min, and that's the range, and you divide by 6, and you get an estimate, and it's fairly crude, but an estimate of the standard deviation. So for this particular problem, 120,000 minus 0 is 120,000. Divide that by 6 and you get 20,000, right? So in this problem, that's 20,000. And then it has a square on it, right? So do that on your calculator. You're always the fastest. What'd you get?
2,654.31.
Okay. Is that what other people are getting? So, rounding the proper way, n is 2654. You just round to the nearest whole number. Is that a big sample? That's a pretty big sample. Why is it so big? Well, it's so big because the margin of error is 1/20th the standard deviation. So I want my error to be 1/20th of what I expect the normal amount of variability to be. That takes a huge sample to do that. So 2654. Okay? I was going to work problem 851, but if I don't work that problem, then I have time to do the other thing that's in this section that I was talking about earlier, and that's small sample confidence interval for proportion. So I'm going to go ahead and do that. Problem 51 is actually a little easier than this one because they just give you an estimate to use for that standard deviation. They say that the standard deviation of farm sizes is 200 acres or whatever it is, and you just put the 200 in there. So problem 851 deals with farm size, number of acres, and they give you a standard deviation. Most of the problems are that way. They'll just give you a standard deviation. But I do know that this problem we just worked with the income is one of the online homework problems. So you're going to be asked to do that. So just remember, okay, I take that range, I divide by 6. That gives me my standard deviation. Okay? So small sample proportions. Remember the assumptions that have to be met for these confidence intervals to be valid. One of those assumptions, maybe I should ask, do you remember what the assumptions were? What was the first assumption? It has to be random sample. Okay. What's the second assumption for a proportions problem?
At least 30.
Now that's for means problems, at least 30, but it's related to that for proportions. At least 15 successes and 15 failures, right? What if you have a small sample? You only have 10 in your sample. Then you don't meet that restriction. There's no way to get 15 successes if you only have 10 in your whole sample. So what this is a way to make the confidence interval valid even in that small sample case. So a small sample confidence interval for proportions is very simple. And this author, Agresti, who's the lead author of this book, is the one that published this in the statistical literature and proved that this works. You simply add 2 successes and 2 failures. In parentheses, I'll say which adds 4 to n. And you say, well, if you have a sample size of 10, you're 5 short on number of successes, and you haven't even started talking about number of failures yet. But what he proves in this paper that he wrote was that if you add 2 successes and 2 to the failures, even though you still don't make your 15, it still works. He shows that it works fine, that the normal approximation is good. So use one prop z int just like you did before, but instead of x, you use number of successes plus 2. So if they tell you they did a sample of size 10 and there were 4 successes in your calculator, instead of entering 4 for x, you enter 6. You add 2 to it. So a number of successes plus 2. And then n equal, what does this parenthesis say? It's the old n, so I'm, instead of writing n plus 4, I'm going to write sample size plus 4. So it's a new n. So in your calculator, you just use one prop z int, but instead of entering the number of successes, you enter the number of successes plus 2. Instead of entering n, you enter n plus 4. And it works. So that's all there is to it. Let's do a quick example of that. I like this one, mostly because college students really like tofu. This is problem 855. It says, do you like tofu? You randomly sample 5 students at your school to estimate the proportion of students who like tofu. All 5 students say they like it. Okay, we know that's bogus, right? But we'll go with it. Find the sample proportion who like it. Okay, that's not hard. What's my n? 5. What's my x?
7.
I'm not ready for that yet, but you're right, it will be in a second. But just read it, it's 5. So what's the proportion p hat? 1. Right? 100% of them. So 100% of them like it. Then it says, part B, find the standard error. Does its usual interpretation make sense? No, and the answer is going to be no. Remember, standard error is square root of p hat, 1 minus p hat, over n. What's that going to be? Well, if p hat's a 1, what's 1 minus p hat?
0.
0. 0 times anything is still 0. Square root of 0 is still 0. So that's going to be 0. So what you're saying is, I have no error. And if you took a sample size 5, you know you got some error. So does the usual interpretation of standard error make sense? No. Part C, find a 95% confidence interval using the large sample formula. So in other words, ignore the 15 successes, 15 failure problem. Just use one prop z int, use x equal 5, n equal 5, see what you get. So that's part C. I'm just going to rely on you guys to give me that answer. The confidence interval, we're going to one prop z int, push the stat button, and then tests, and then go to one prop z int, and enter x equal 5 and n equal 5. Set your confidence level at 95%, 0.95. And Delaney, you got it?
There's 1 and 1.
1 to 1? Why is it that? Because the standard error was 0. So the margin of error is 0. So you got point estimate 1 plus and minus 0. So it goes 1 to 1. Again, doesn't make sense. Yeah?
What was the confidence?
95%. So part D says now do it using Agreste's small sample confidence interval. Use a more appropriate approach and interpret the result. So now redo it, but use x equals 7 and n equal 9. Add 2 successes and 4 to the sample size. And tell me what you get. Did you get it, Jordan?
Yeah, I don't know if it's right though, it's kinda weird.
Well, it will be kind of weird.
Okay, I got 0.50617 to 1.0494.
And you didn't like this upper end, did you? Because that's bigger than 100%, or bigger than a proportion of 1. So what we do in that kind of a case is we would just stop it at 1. We'd say, well, I know I'm 95% confident somewhere between 50% and 100%. Now that, again, that's not a very useful interval, is it? 50% and 100%, well, that's because you took a sample size 5. You can't expect to be very precise. But at least it's a valid interval, meaning it covers 95% of the time. Whereas this one, that makes no sense. Okay? All right. That's all the time we have. So section 8.3 is due tonight by midnight. 8.4, which we just covered, will be due Friday by midnight.